In this video, we'll see how near numbers can be mined out of the standard logical definitions of calculus. This video is principally aimed at viewers comfortable with these formal definitions. For those not yet comfortable with these definitions, this is just a peek ahead. The first definition we'll consider is that of the statement, limit as x goes to positive infinity f of x equals positive infinity, which we'll deconstruct just far enough to see the near numbers hiding inside. Note that using an equal sign with positive infinity is an abusive notation forced on us if we try to stick to limit terminology. No such problem will arise in the near number context. Let's look at the four lines of this definition. The set of x with x greater than n forms an interval in the domain of our function that should look familiar. And the there exists n greater than 0 allows the value of n to vary, which we interpret as motion. Similarly, the set of values f of x with f of x greater than m paints a target interval in the codomain of our function, and the corresponding for each m greater than 0 gives us motion there. We can use near numbers to express the same statement in a much more structured manner. Starting from scratch, this near number statement says, if we take the near number positive infinity, and we apply the function f to it, transforming it into a new and possibly differently shaped near number, the result fits into the model given by the near number positive infinity. The only new elements here are the near numbers and the arrow, which have independent meaning and can be studied in isolation. The two positive infinities have their own meaning independent of the function or arrow, and the arrow is a relation that either does or does not hold between any two near numbers, with or without a function being involved. But it's the very same concept in every case, and we'll study it carefully. Compare this to the limit statement, which has meaning only as a whole and has a definition that's an awful lot to swallow all at once. Near numbers will allow us to better understand the subtleties of limits even without the formal definitions. If or when we do proceed to logical definitions, we'll have a set of concepts ready on hand to use as building blocks. This will allow a more gradual, structured approach to the definition. It's important to note that the logical definitions we arrive at will not change. We'll just have a better way to conceptualize and express them. Our second definition to consider is that of the bread and butter statement, limit x goes to a f of x equals L. This has its own implicit notational subtleties, such as the fact that x is never allowed to equal a for the limit, and nothing in sight actually needs to equal L for the limit to be L. Equality is not the concept at hand. The set of x between a minus delta and a plus delta, accepting a itself, paints a simple picture in the domain of our function. And the there exists delta greater than 0 varies the value of delta, squeezing the picture toward a. The set of values f of x between L minus epsilon and L plus epsilon paints a very similar picture in the codomain of our function, this time with the point L included. And the corresponding for each epsilon greater than 0 makes that squeeze in. Using near numbers, we can state this more concisely and precisely. We can read this much as we did our last near number statement. If we take the near number a plus minus, and we apply the function f to it, transforming it into a new and possibly differently shaped near number, the resulting near number fits into the model presented by the near number L plus minus dot. Other than the different near numbers involved, this can be understood in exactly the same manner as before, allowing us to focus on the key point of the meaning of the arrow relation. Note that the exclusion of a and the inclusion of L are now explicit in the notation, and the misleading equal sign is gone. We can still say the limit equals L if we like, but the squeezing of the near numbers that got us there is front and center rather than being buried. It bears repeating that the logical definitions we arrive at when we finish will not change, but we can express them all in a unified way using near numbers. Our next videos will present near numbers from start to finish, functioning as a curricular supplement for any interested student or teacher of calculus. Please share this video and check our blog, where we'll announce new videos and discuss questions that come in. And don't hesitate to use the contact email below if you have any questions along the way.